Hello, everyone. Right, okay. Let's get started. So there's quite a lot to go through, and I kind of reorganised the slides last night, so we're going to figure this out together. So this is exploring the world of unbranded 4G modems, and this talk really is about a story on looking at, I suppose, what I found on AliExpress and taking it apart. So what is this all about? I was working on a project that required a 4G modem, and I found a bunch of these online, and they're really cheap. They're £5. They're just USB modems you can plug into a computer, and you can access the sort of mobile network. And for £5, that's a pretty good price. And I started looking. Well, I bought quite a few of these, and I started looking further at them, and noticed that they had Qualcomm chipsets in, and they had memory and storage. Why would your modem need storage? Why would it need memory? That's a bit strange, right? It's just a 4G modem. That's, quite odd. And I started looking further at these, and they have chipsets in them that are from mobile phones. So the Qualcomm 8916 is the same thing that's in a bunch of smartphones. And it turns out it's a lot cheaper to use parts out of mobile phones than it is to actually remanufacture a USB sort of modem. And what's really cool about this is the hardware that would be actually in these would be the same sorts on a mobile phone. So I thought, why not? Could we repurpose these and turn them into like an offensive security tool? So this is what really the talk is all about. We're going to basically look at these, how they currently work as is. Look at what research is online. There's quite a bit of information, and this is kind of, I suppose, the story on what I ran into and then what others have found online. We're going to build some firmware for it, and we're going to kind of do a very high-level run-through of how to build some firmware for these devices that's custom compiled. And then we're going to try and turn it into a Dropbox where we can plug it into a machine and see if we can inject keystrokes into the machine and then get C2 traffic through a USB modem. Let's see if we can get it working. So in terms of past research, now, when I started this project, it was kind of, as I was going along, there was more and more bits of information that I found online, and I've kind of pieced together some key bits here, but effectively these modems have an entire community around them called OpenStick, and it's really worth checking out because there's a lot of information online. A lot of people have built different projects, so one of the main ones... Oh, I've got a laser pointer here. One of the main ones here is the OpenStick stuff, which is almost pre-compiled firmware you can flash onto the device. And when I was looking around, there wasn't really any, I suppose, firmware you could find that was entirely compiled by hand. It was all these random sort of binaries you could flash to the device, and you don't really know what they do. So I thought it might be quite cool to actually do that ourselves instead. So this is what the modems actually look like if you take them apart. I've got actually one here, so that's what it looks like. This is what they look like when you take off the plastic cover. They're really small. It's about just bigger than a USB stick. It has a shield on top, but you can just sort of pop that off. And we can see there is the Qualcomm chip we were, I suppose, wanting to look at. What's quite cool is on the left here, there is a flash chip. So that's a 4GB eMMC flash chip. But it also has 0.5 GB of RAM in the chip in itself, in just one package. So everything on the top left there, in the corner bit, all of that is effectively a mini computer. So you've got the processor, you've got the RAM, you've got the storage. So that's quite neat. And then everything else around it is just supporting peripherals, I suppose. When you actually plug it in to your machine, it comes up as a USB Ethernet gadget. And it will also come up as an Android debug interface. And if you Nmap scan it to see what's on there, there's a web server where you can manage stuff. There is a DNS server, and there's a random other port that I've not looked into, but go buy a modem and have a look. It's probably quite interesting. And yeah, if you actually want to root the device, in this case, just running ADB shell would drop you into a root shell. So that's the end of the talk. We've rooted them. Yeah, and what's quite cool is when you do actually run ADB shell on this, you can get sort of Linux systems that are using ADB you can log into, but a lot of the time ADB is used for Android devices, and when you log in, we can see this is running Android 4.4, and this is effectively an Android phone just without a screen. Before we start, I suppose, doing anything with the device, it's always worth backing things up. So there's a thing called Qualcomm Emergency Download Mode, or EDL for short, and it runs a thing called Firehose, which has a protocol called Sahara in it, which is a Qualcomm-specific thing where you can almost access underlying storage on a device. So if you can trigger it with software or hardware, you can get it into a mode where you can almost read and write from bits underlying on the device, which is kind of what we want to do. Interestingly, the fact that this, I suppose, we've almost gone by a slide. Yeah, so the fact that this in itself is accessible is quite a key thing. So the emergency download mode stuff will only work if the device doesn't have cryptographic keys embedded in it, or you can use kind of something that is signed. So the idea is a manufacturer would protect it by putting their cryptographic keys on the device, and it means you could only load your loader and your thing for emergency download mode that is authorized by you. So it's kind of protected in that way. But in this case, there was no actual keys protecting the device. So you can almost load any bit of code onto the modem, and then you can read anything out. And what you can do with that, with these off-the-shelf tools, is you can basically just read the entire flash. So there's a few sort of key commands that you can use, but I took a backup of the entire device before breaking it and bricking it. But with that, we can actually look around and see what's on the device, because we now have a copy of what's on the flash, and we don't need to take it off. So if you run a tool called binwalk, it's quite a common tool for binary analysis. It will just look for signatures, really. It's kind of like an antivirus, really, where it's just looking for specific signatures, but will look for files and other cool stuff. It is just a sort of a GPT partition table that has a bunch of different partitions, and these are all the partitions there, which the device uses to actually come up. And there's quite a few it uses to actually bring up the device. So, yeah, the actual partitions here. So you've got a few like RPM, TZ, which is trust zone, Hype, HYP, that's a hypervisor. So that's a Qualcomm hypervisor. So the USB modem is a hypervisor, which is cool. This is kind of how the device boots up and what the partitions, or how the partitions are used. So this is quite important later on, so this is just to give a bit of context. The PBL is burnt into that Qualcomm chip. You've got a SBL1, which is kind of the first stage bootloader. That goes into then Trust Zone, so TZ, that will load that. You've got then the hypervisor, then you've got Qualcomm's little kernel, or A-boot, it's just the Android bootloader, and then it will load the Android kernel and the rest of the actual device. So this kind of aligns with what's in the sort of partitions here. So to actually read things on the device in the partition table, you can just DD them out and you can have a look. So you can almost rip out that specific bit of the firmware and see what it's doing. You can mount it on a separate machine, and in this case you can just read what's on there. So there's a few different files. One bit of research online mentions that if you can't find or you can't get ADB access on these devices, there is a HTML page there called USB debug. When you go to that, it will actually open up the ADB interface, which is quite nice. So, what does the actual web UI look like? You've got a login page. The credentials are quite weak, but if you just navigate to the main HTML site, it will log you in. And what's kind of interesting about this is you can then sort of look around the device, and it just looks like a normal web management page, to be honest, for a router. There's nothing super special on here. I'm sure there's more to look at, but there's nothing super special. What was interesting, though, is the device information had an IMEI number. So that's kind of what's hard-coded in the modem, and that's what the modem uses to authenticate, well, not fully authenticate, but identify itself to the cell tower. You could change that. Now, I didn't try and change it, but the text field was editable. And in the UK, that's very illegal to change, and a lot of modems don't allow you to do that, but I just thought it was interesting that it was an editable box. So it's probably worth looking into that more, because you shouldn't be able to do that. What else? So we know it's an Android device, but where's the screen? It's effectively a phone, but we don't have any screen. So there's a common tool called SCR-CPY that's used in mobile testing, and the idea behind it is you can almost run this tool on a host, and over ADB it will allow you to see your phone screen. This doesn't work because the Android version running on the device is too old. But what we can use is a library called Minicap. So this is designed for headless, I suppose, like Android farms, where you've got loads of devices for testing, and this sort of captures the screen of all of them. This works on really old versions of Android, which is awesome. I think it's down to like 2.3 it works on, and we're running 4.4. So, we can put together a quick tool to use this, and we can actually see the phone. So it just has a default Snapdragon splash screen, and it's pretty much just a phone, which is quite cool. It's all in Chinese, and there's a few different test apps on there as well, which is quite interesting. Again, I didn't actually look into these, so buy one, have a look. It's good fun. There's a few other things as well, like a Hello SMS app too. I've not looked into that either, but it's worth checking out. And then, you can use it as a normal Android phone. So that's, I suppose, a very quick way what the devices actually look like when you buy them, how they work, and what's running on them. Let's actually get our own thing going. So Linux, when it boots up, you have, I suppose, three main things here, and I'm kind of summarizing this in a quite high level. You've got all of the initial first stages, so that's the PBL stuff, the first stage bootloader, the trust zone stuff, the hypervisor, and all of the, I suppose, subsystems that are coming up. You've then got Qualcomm's LK, which is Qualcomm's sort of bootloader that's quite proprietary, and then you've got the Android kernel. And the plan is we're going to try and almost replace the Android kernel with our own, and then replace Qualcomm's little kernel, Qualcomm's bootloader, with something that's more open source that we can, I suppose, try and actually use. And then once we've got our own kernel working that we've compiled, let's build a quick init script to actually see if the device will come up, and then we'll try and take that a step further and see what we can do. So to actually compile the kernel and get it working, this is, again, summarizing quite a bit, but it is relatively straightforward like this. You can download the kernel from the Linux GitHub repository. There is mainline support for this chipset in the kernel. You can use a default configuration, and then you can just compile it, and it will throw you out an image at the end. There are two other things as well we need alongside this, which is just a configuration for how the LK bootloader should load this up. And then we need a device tree. If you're not familiar with device trees, they're quite cool. So on regular PCs, you plug in a device, it will auto-detect it, and it will sort of come up, and your PC almost knows where everything is internally, and it can figure it out. On embedded systems, you don't really have that luxury, so you have device trees instead. And these are almost descriptor files they describe really how everything's laid out. So a small embedded system, for example, can't really work out what's connected to a serial port. So you use this to almost tell it what device is on the other end. And this is kind of how you structure how the processors, I suppose, operate, how memory comes up, and how different bits are organized. Fortunately, there are off-the-shelf, I suppose, versions for these devices you can get online, and we can also rip out from the original firmware the device tree, because it is just a file that's in that firmware dump that we got. So that kernel that we compiled and put together, along with the device tree from the original device and the config file, I tried to actually flash it using the emergency download mode again, back to the device. And it said that it was too big. So it was 40 megabytes, but the partition size was only 16. And how do we actually get around that? So we almost want to rebuild what the partition table looks like. And this is something that the sort of OpenStick builder tools do as well. It's quite a nice way to do it. So we almost want to overwrite, really, what the device partition table looks like, and I suppose give us more space. This is going to wipe everything on the device, but we can reflash the bits we want back on. So to get it into a point where you can actually do that, this is the example partition table that we're going to flash here. To get it into a point where we actually want to do that, we can delete the bootloader. We can delete the kernel, and we can restart the device. And the Android bootloader is going to panic and put us into fast boot mode to allow us to actually use fast boot to then flash stuff on the device and modify things more. Fast boot is, I suppose, another level above the emergency download mode, and it will allow you to interact with things a bit better. So, put together this partition table. Again, it's pretty much the exact same as what the OpenStick builder stuff does, and then flash that to the device. And because it's actually reset what the device does, or what's in all of the partitions, we need to then go through and rewrite back our sort of core partitions. So all of them initial first stage bootloaders and the trust zone stuff and the hypervisor stuff, we need to put it all back on. And then when we actually turn on the device, we can see that it does start to boot up, and we sort of get some text out, but it's not actually going into the little kernel bootloader because we never put that back on. What we can do instead, so this is the open source bit, there is a thing called the little kernel bootloader, LK2ND. It's an open source version of that we can use instead and just flash directly onto the device. This was, again, quite straightforward to do. You can just compile it. It has mainline support for this chipset, and you can flash it in the slot of where Qualcomm's little kernel was, and it just kind of works. So then when we start up the device again, we can see it gets a bit further. It goes into their actual bootloader, but it says no boot image. So at that point, what we can do is we can try and flash... Oh, sorry, what's going on here? We can try and flash our kernel onto there. So I tried to flash the actual kernel onto the device and realized that it said there was sort of no bootable image. And I thought that was a bit strange. And when it tried to boot up then a second time, it said it can't boot ARM64 with the old SCM calling conventions. And this is because that initial Android, I suppose, operating system we looked at was all 32-bit, and everything on this device was 32-bit. So this is kind of what the boot process looks like, and we've compiled the kernel for 64-bit, which is a massive pain. So the sort of two options you can do here to really fix it is you can, I suppose, recompile the kernel to 32-bit, or you can try and upgrade, I suppose, the rest so the device works on the 64-bit mode. And that's kind of the plan on where if we can upgrade these two, or, well, these different bits of the device to work on 64-bit mode instead, could we actually get this working? So on the device we've got, we don't have any 64-bit binaries or any 64-bit, I suppose, bits of firmware. But luckily, there's development boards out there that do. And we can almost take the firmware blobs from them and flash them onto our own device that do support 64-bit. So we can flash them on there, and it just kind of works, which is quite cool. So we're now using the actual 64-bit stuff, and we have a Linux kernel that actually boots up, and it says somewhere on there it's compiled with on Kali Linux and stuff. So we have the kernel, it works. This is our own code that we compiled ourselves, and it's running on the device. But it doesn't actually run anything. And this is, I suppose, one of the quite common misconceptions, I suppose, with Linux. If you have the Linux kernel, the only thing it really needs is just a single init process to jump to. You don't really need any, I suppose, super fancy operating system on top of it. You just need one single binary which it can run. And in a lot of times you have sort of init processes from this. So the systemd, for example, is a single init process that the kernel jumps to. But we could just look into writing our own. So a simple C script that just says hello world or something like that. You can compile it, put it on a file system and call it init, and then actually flash it back to the device. And then when we start it up, it just comes up with our hello world. So that's kind of our own code running on our own compiled Linux kernel, running on these 4G modems, which is pretty cool. But was quite a long-winded process, right, to actually do that. And so many things went wrong. And is there a better way we could actually, I suppose, build this out? So there's a tool called Buildroot. Buildroot in itself is amazing. It's worth checking out. And there's quite a few different, I suppose, tools out there like this. Effectively, what it does is it allows you to build Linux distros, I suppose. That's probably the easiest way to explain it. You tell it what system or what board you want to target. You tell it what packages you want. You tell it what kernel to use. And it will go off and almost build a cross-compiling environment for that. It will build all the tool chains for you. And it will compile all the things. So if you can put together a config or a custom board to support these modems, then you can almost use Buildroot to compile the rest of it. So you can also, do things like applications as well and compile them. So to actually get it working, we just basically took everything we've just done, turned it into a Buildroot config, told Buildroot to go ahead and make it. It went off, built all the images for us, and at the very end, we just flashed it back to the device. And there we go. We've got a small sort of Linux shell, very minimalistic system running on these modems, which is really nice. Something I should probably say is on... I actually have one, so I can show you. Okay, well, I did have one. It's in my bag somewhere. On the actual device, there is a serial port. So it's a 2 test pads on the side, which is transmit and receive. And this is the serial console we're looking at here. So I just tacked onto them. But right now, we don't have any Wi-Fi support. We don't have any... it's not actually being a modem. We don't have any other subsystems going. So it's just basically a Linux shell, and that's about it. So to actually get Wi-Fi going, that's, I suppose, a bit more difficult. So you have WPA supplicant, which is commonly used on a lot of systems to interact with the kernel modules that handle Wi-Fi. But on these, it's a bit stranger. So these devices have custom firmware and custom, I suppose, blobs that are used to actually bring up the Wi-Fi chipset, because it's almost all part of one system. So we need to almost recover them from the original modem or the original firmware. But in the meantime, I enabled WPA supplicant. I decided to use Network Manager. I did initially, while I was testing, try and do this by hand. It worked fine to get it working, and then I realized to make any single change, I had to edit like 3 scripts, and that was too much time. So Network Manager, you can write one config file that tells it to, here's the interface, do me a thing, and it will go ahead and I suppose do that for you. Yeah, and from that as well, to actually get the Wi-Fi modem, the Wi-Fi driver working, you need these, I suppose, custom blobs that are actually used to bring up the Wi-Fi hardware. And these are on the original modem. So I basically just took the original partitions that were on there for the modem, brought them over to this new one we're building, and mounted them and loaded them. This is quite a common technique. Again, this is, I suppose, the thing that with these devices everyone seems to do. And there is scripts out there for other boards and other phones that do this exact same thing, where the calibration data and the blobs for this firmware is stored sort of separately from the actual operating system. But yeah, so brought them over, loaded the, I suppose, firmware up, or loaded these into memory, loaded all of the kernel modules that are for these Wi-Fi, or the Wi-Fi module on there, and it effectively just worked, which was kind of nice. This is, I suppose, making a long and short example of actually how much work it took to get it into this state. But with Network Manager, that speeded things up a lot. So we have Wi-Fi. It now pretends to be an access point, and it works. We can connect to it. Awesome. So we're getting a step closer to actually building that Dropbox. LTE. So to get LTE going, there is I suppose, a tool you can use called UQMI, which allows you to interact with modems directly. I initially got this tool going and set this up with, again, the same kind of approach with the Wi-Fi side of things. You need to load in the firmware blobs and calibration data from these partitions to get the LTE modem going. And I tried to interact with it. And it did actually work. So you could use this tool to see local cell towers. You could see it actually had signal. It was available. It did try to connect to some. But I kept running into an issue where it would register with a cell tower, it would lose a handle on it, and then it would just try and roam to other cell towers and then get blocked by them because it's not the right SIM card for that other cell tower. And there's a better way of doing this by hand, which is using a tool called Modem Manager. So Modem Manager is an extension to Network Manager, and it just allows you to control your modem more efficiently, I suppose. So I set that all up. There was one other thing as well, which was quite a forgetful modem. Every time it would turn on, it would look for 3G networks to start with, and then would fail. And in the UK, they're sort of being deprecated now, so I had to force it to connect over 4G to actually reach a cell tower. But after setting that, it worked. So you could actually connect to a cell tower. It comes up as connected. You can ping outbound, so we have internet, effectively. So we've got Wi-Fi, we've got LTE. Let's actually get USB networking going, so we can make it become, I suppose, a USB gadget and send network traffic over there as well. The Linux kernel has support for these things called gadgets, which are, I suppose, small modules that allow the device to pretend to be other things if it has support to do that. And there's an entire subsystem built around this. So you've got things like Ethernet, HID, so keyboards, you've got audio things, for example. So there's loads of different stuff you can do. But an easy way to actually manage this, again, this is I suppose, a shortcut approach to actually implementing it. You can use an off-the-shelf library, so libusbgx, that interacts with, I suppose, or provides the userland implementation of this USB subsystem. And then you can use tools like GT, so gadget tool, to allow you to load configs and then almost, I suppose, bring them up as gadgets. We can create a template to tell it to become a USB Ethernet gadget. We can tell it to, we can tell it to be a USB Ethernet gadget. We can build a network manager config, and we can tell the device to load this config and bring it up. And it just appears as a USB interface. So from that as well, when we plug it into a host, we can, because Network Manager's there and it's handling DHCP4s and all of the other networking things, I suppose, in the same way it did for Wi-Fi, it assigns us an IP address and we can log in locally and it just kind of works. USB HID. So getting this to actually pretend to be a keyboard is quite interesting. So you can just enable support for I suppose you can enable HID support in the kernel, and you can use the gadget tool as well with a config to pretend to be a keyboard. I called it Trustworthy Keyboard. I thought it was quite amusing. I was debugging this on VMware, and every time it would pop up saying a trustworthy keyboard is connected, it made me laugh. But you interact with this with a device which appears on the gadget. So it almost shows up as /dev/HIDG0, and you can pipe it almost. It's pretty much the HID protocol, really. You can, from the HID usage tables, you can give it what I suppose a keyboard would send, and it would pipe it directly to the machine. So we could push the A key and then we can release them. Interestingly, so when you send a command to it, like pushing a key, you need to tell it you've released a key, or it will just continually press some stuff. So timing is quite important, but what we can do is, so this quick example here where we're just pressing the A key and then releasing it, we can just put that in a small one-liner script, and we can have it press multiple keys, I suppose. And that's almost our very basic sort of keystroke injector. But we can take that a step further. So we can basically put that script behind a web server, and we have Wi-Fi, we've got USB, we've got LTE, so there's a few different now methods we can reach this device. And we can almost use this as an interface to send keyboard commands over. So you then got a web UI, so put together this quick web UI where you can almost send commands to the machine it's plugged into. I was connected to this over, I think, the Wi-Fi, so this was controlled by another machine, and you could, interact with the device just from this. You could take that a step further again, so like a USB rubber ducky where you've almost got ducky scripts, put together some sort of small macros to actually write things in line, I suppose, so we can actually type things and get things I suppose a bit more efficient with the timings instead of having to manually type it and press enter ourselves. And so that's kind of the fundamental building blocks of what we're going to put together. And let's actually make the Dropbox. So kind of what we've gone over at a high level is compiling the kernel, building the distro, LTE support, Wi-Fi support. We've put together the USB gadget. We have hopes and dreams, and we now want to actually make a sort of a device that will allow us to make a USB Dropbox, I suppose. And the kind of idea behind this is we've got a single USB modem we're going to plug into a machine, a target machine somewhere, specifically maybe like an air-gapped environment where it doesn't have access to outbound internet and there's I suppose no way to actually get traffic out the machine normally. We can get the USB modem to inject keystrokes into that device, get it to trigger an implant somehow, and then almost could we tunnel C2 traffic out the device through the USB modem outwards. So we've almost got out of bounds C2 exfiltration or traffic coming out. And then to actually reach the device, I just connected it to a WireGuard server. So it's, I suppose, a lot easier to reach it from the other side, I guess. To actually get WireGuard going, so the only thing we've not done, I suppose, here is actually setting up WireGuard. That, again, is a kernel module. You can just enable WireGuard. You can then give it a configuration, tell it to bring up the WireGuard interface, and because it's baked into the kernel and just needs a configuration and where to go to, it just works again. So that's kind of the getting WireGuard going. And what's kind of nice about this is we can now access stuff on the other side of the WireGuard tunnel, so we can access our C2 server, but from there we could also connect back to the device, because we've got that sort of web, I suppose, keystroke injection UI going. We could just connect back then from wherever we are on the internet, and we can connect back to the device as it's plugged in. So we can now control this over the internet, over LTE. So one of the, I suppose, last things we need to do really is we need it to come up as a keyboard and then as an Ethernet adapter. But the timings of this can be quite awkward, so we could just bring up both at the same time. We can have it be a sort of a composite USB device with just two different interfaces. We could have it be the HID device and the network gadget at the same time. And again, gadget tool, make a configuration for it, just add what you want in there, add what functions you want, and it kind of appears as that, which is awesome. One, I suppose, final thing before we actually put things together. Currently, when you plug the device in, it just shows up as a USB network device. But we can't actually get any traffic out of that. We've not set up any routing, or we've not told it actually how to handle packets on what we want to do. So we can use IP tables to almost tell it to any traffic coming from the USB 0 interface from the actual host, send directly through the WireGuard tunnel. So the device or the host can't talk to the internet, but it can talk to that one C2 server we've got on the other end of the WireGuard tunnel. And yeah, for the sort of proof of concept, I use Slither because it's just one go binary. You can run, it'll generate you more binaries. It's quite simple and straightforward. I did initially try to download through the actual WireGuard USB interface on the host, get the target machine to download the implant. And over 4G, it just takes so long to actually do. Maybe I had bad signal, but I thought it would be easier to download the implant on the actual 4G modem and then have the, I suppose, keystroke injection side of it, download it from the modem, which I thought would be a bit quicker, but turns out it wasn't super quick because it's quite a slow USB interface. So putting that all together, this is kind of what it looks like. On the bottom right, we can trigger a macro that will run the keystroke injector. This is not a, I suppose, super sneaky way of doing it. It's just writing it and dropping it on disk, and then it's loading it directly. A lot of things would catch you here, but it's, a cool proof of concept. So the keystroke injector has worked. It's told it to download our implant from the USB modem. It's then launched it. On the Slither terminal at the top, we can see that we've got the implant come back through the USB modem, and that in itself works. That kind of shows that we've got C2 traffic going through the modem when we're using an targeting an air-gapped machine. So, cool. We built it. We put it together. I'm releasing all of this online, so you can find it on GitHub. I'll probably release it this weekend after SteelCon. And it'll be on the recording as well. But hang on a second. There was something we forgot. Or did anyone catch that?
Go back, please.
There you go. Give it 3 seconds. Pause for... Yep. I'll go in 3, 2, 1. Wait a second. There was something we forgot. What was that? There's a USB webcam gadget in the Linux kernel. When was this hit? I probably looked at this so many times and completely overlooked that this exists. And yeah, there's USB webcam support. So, if you've got a conference system, right, a really fancy one that does sort of video tracking and detection and processing, a lot of the time these are just embedded Linux systems that are using this gadget. So when you plug it into your laptop, they're pretending to be webcams, but it's actually a Linux system and it's piping all the camera data back through that. So could we actually, use it as just a random funny thing? What could we actually do with this? So there's a library out there called, I say it's a library, it's more of a tool. It's called UVC Gadget. So when I suppose you enable this webcam subsystem, it exposes a video interface, which is almost the raw underlying, I suppose, camera that's coming up with Linux. And you can use UVC Gadget to interact with that and handle all the control requests and handle the video, I suppose, going to the device. So this is kind of what you would use to almost pipe in video footage and stuff like that to get it to end up on the camera you're pretending to be. So I thought, just as a small side project, it might be quite fun to mess around with this. So the normal way you're supposed to do this, or the easiest way you're supposed to do this, is you can use UVC gadget to pipe in an image, and that will control /dev/video, which will end up on the host. So you can almost pass in static images on the camera, right? But could we do it in a different way, where we have almost a still image that we repeatedly send to a loopback device or some kind of virtual video interface, and then pipe that into UVC gadget, and then that ends up in the camera. So it's almost like even though it's a still image, is it a video feed? And yeah, we can. So you can take an image, you can give it into like a frame feeder tool, and you can tell that to almost pipe it to the UVC gadget, and yeah, it works. Something that's quite amusing is when you plug this into a device and you're currently on a call, sometimes Teams will auto-switch to the camera. So tell me how I know this, right? So yeah, I thought that was really amusing, but can it run Doom? So this is where all the talk's going, by the way. It was like not for the keystroke injection thing, but there's a thing called Doom Generic, and that takes the Doom engine. It's a repository online. It's really good. It takes the Doom engine and it almost makes it versatile to use in anything you want. So it kind of exposes how you render frames, how you take input, and it's down to you to implement that. So the idea is it allows you to put it on things that you wouldn't normally, I suppose, implement it on. So we can take that Doom Generic engine and we can almost patch in I suppose, for it to write to the frame buffer that we were initially doing with that still image. And we can pipe that to dev 1, which UVC gadget will pick up, and then pipe to the camera. But I kind of got all this going and realized I suppose, a big oversight. You've got a USB camera. How do you actually control it? Because you can't really control things on a camera. So we've got the Wi-Fi support, we've got USB support, we've got LTE support. I thought, why not make a small control interface that's over LTE? So you can plug in the device and control it over LTE. And yeah, putting that all together, you can almost control Doom remotely for a USB modem that's pretending to be a camera running Doom. And it works. So, yeah, that's the talk. Thanks for listening. Any questions?
Yeah, I've got one, Aaron. So that's, for all intents and purposes, a mobile phone. Are there any other interfaces you can't explore? Maybe a microphone?
So, funny you say that. There was a microphone app installed on the, I suppose, image, the OEM firmware on this, but there wasn't any actual hardware on this device for a microphone. But there are a few others you can buy. So, I mean, this is kind of, let's actually get this out of the box. Well, we've got 5 minutes, we'll be fine. There are others out there. So I got, here's another one that has kind of cables attached to it. But you can get other modems that run the same thing. And this one has a battery. It's a cable shouldn't have fallen off. But yeah, you can get other modems. They come in various different form factors with different features. And it's worth checking out what is out there online. There is really no brands to these. They're just kind of generic, I suppose, devices that other manufacturers then make spin-offs of. So you could get loads of weird and wonderful things with different features in, so it wouldn't surprise me if you can find other stuff with these. So it's worth checking it out.
When you were setting up with the test Windows PC, did it try and stop you at all when you were setting keystrokes to it with USB?
No, it didn't. So yeah, the keystroke injection stuff's quite, I suppose, in a way, a difficult one to protect against on a stock Windows PC. You can implement stuff where you filter by like the PID and VID of the device, but ultimately, is it a keyboard you've just plugged in? Because for all intents and purposes, that is a keyboard as far as the OS is aware. So there are things you can do to try and detect it, but I think that's equally for example, a USB rubber ducky would have the same kind of problem, really. Windows with a USB ribbed up would have the same problem.
I just wondered if you did an analysis on the firmware that was there when you got it new, and if you spotted any unexpected behaviour in that.
Yeah, so I did a little bit of analysis, but I'm not going to say I did a sort of a proper deep dive on what's under the hood. There's a lot of different test scripts on there, and there's a lot of different things that almost look like they're for other devices, but it's been removed or it's no longer actually used on these. So the firmware in itself is, I would say, made for a large selection of devices and contains a large, like the microphone application, for example, contains a large selection of devices with different features. So yeah, the microphone thing it might actually be used on something else. The Hello SMS thing as well might be used on something else. I didn't really see these in use, but it's worth checking them out. And yeah, I would recommend going to buy some of these because they're good fun to look at.
Got a question for you on the hardware side of it. So you mentioned the board or whatever, which you device elsewhere, but have you noticed any way of attaching peripherals to the actual device? Because obviously it's a mobile phone, so you can actually attach a camera you actually attach. So,
great point. It's not just a USB gadget. That is in itself a USB controller. That is on the other end of that USB stick. So when that starts up by default, that's a USB host. So it's not pretending to be a gadget, but it's, I suppose you can almost plug things onto it. People have made online boards that you can plug it into that expose that USB interface where you can connect things to. So with that, you can almost attach a USB hub and then like an Ethernet chip, and you can connect it with Ethernet. So for the price point, they make sort of great small little devices you can use because the price of RAM's going up, and I'm pretty sure the memory in that is probably more expensive than the actual device. So it's yeah. Any more questions?
Have you got a blog, or is it the GitHub that documents any more of this, or where to find this?
There will be a blog. It'll be going up on the Pentest Partners blog at some point soon when I write it. Yeah, that'll be going up online soon. But yeah, you can check out on GitHub. There'll be the repositories for these that will have bits of information on there as well. Any more questions? No. Thank you for listening.